Good evening. I am Yashodhan Talekar from BEENTC. I am here to present on regularization. In this video, we, we will be saying what is the regularization, what are the different types of regularization, differences between their types, what are their advantages, disadvantages, and compare their accuracy score. Regularization is one of the most important concepts of machine learning. It is a technique to prevent the model from overfitting by adding extra information to it. Regularization basically adds a cost on the optimization function. It can be also termed as a technique to improve generalizability of a learned model. There are two types of regularization, L1 and L2. Also, L1 is also termed as lasso regularization, and L2 is also termed as ridge regularization. So, if your trained model, has a better training score and performs well worst on the test data or to the data which it hasn't seen, then we can term your model is overfitting, and this problem can be solved by regularization. Regularization works by adding a penalty. To see which penalty it adds, consider a linear model of a linear regression where we get equation as y equals to beta naught plus beta 1 x1. So to calculate the square sum error, penalty is added to the square sum error. In the second figure below, you see the penalty is termed as lambda integration of all the coefficients of the linear model. When lambda is equals to 0, the penalty has no effect and the result is almost will be near to the squared error sum we calculated above. However, as lambda tends to infinity, the impact of the penalty grows and ridge regression coefficient may also approach to 0. So choosing this lambda value is very critical. Ridge regularization and lasso regularization are two types of regularization. Ridge regularization adds L2 penalty. It uses squares of the coefficient as its penalty. Hence, it is also termed as L2 norm. All the coefficients in L2 regularization are shrunk by the same factor, and due to the square term, we never get 0 at the last term, but the value can approach near to 0. Lasso is another version of regularization in which the same function is minimized, which was used in term of ridge regularization. It is clear from the variation that it uses modulus of the coefficient. It can be also termed as an extension to linear regression. Penalty used here is L1 penalty, and this penalty can go to 0, and hence it leads to shrinking of coefficients. The key differences between ridge and lasso are ridge regularization can be close to 0 but cannot be 0, whereas in lasso regression the penalty can lead to 0 coefficient. Due to this, the model as well as in the model some feature can be deleted and hence it can be used for feature selection. As the coefficients do not turn to 0 in ridge regularization, it is mostly used to reduce overfitting, and it does not delete any features present in the model and includes all the models. Ridge regularization is computationally less expensive than lasso, whereas lasso is more expensive. Advantages of using regularization are to avoid overfitting. They add enough bias to make reliable approximation, and when in the case where number of predictors are more than number of observation, this technique performs well. Then disadvantages are some types of regularization shrink the coefficients to zero, which may lead to deletion of feature, and some are unable to select the features. Comparing accuracy score. So in a problem I solved, comparing the score, I found that when I used linear regression model, and the score obtained for training set was 68%, and same model when checked for testing purposes, the accuracy was very worst, which was almost 14%. Next, I used lasso regression model, and after fitting this model to the data set, training error and test error were more than 65%, and the result was very high compared to linear regression. Similarly, for ridge regression, the training and test score was almost equal to 65%, and there was a large difference when compared with linear regression model. And so implementing regularization in Python. So at start, I imported all the libraries. Dataset was imported. This dataset was downloaded from Kaggle. This is a Melbourne housing dataset which includes the pricing of house and columns to support those prices. The shape of the dataset is 34,000 rows into 21 columns. So most of the rows, like for example date, were not useful for prediction of the price. So only useful rows were selected and the dataset was filtered. This is our filter dataset, and the shape was reduced from 21 columns to 15 columns. To fill the missing values, so there were these number of missing values in the dataset, and some data, so to fill the values, fill na method was used, and some values from the dataset such as bedroom 2, like if there is na present in bedroom 2, you can't enter mean over here, so 0 needed to be entered. So similar columns such as property count, distance, bedroom to car, bathroom. If you don't have a car, so you can't enter mean or fill it with mean. So 0 was filled. And similarly, now in the remaining data set, building area and land size values, missing values could be filled with mean or median. So the missing values were filled with mean. Since data set was large, I dropped some rows because filling this missing volume, it wouldn't matter much. And so some data set over here was categorical and needed to be encoded using getDummies function from pandas library. This task was achieved. And then label and dependent data was separated into x and y variable using train test split class from the sklearn library. Data was split into train test. Next part was pretty simple and repetitive, following the traditional machine learning process of importing and creating a variable, creating an object. So from linear model class, from sklearn package, linear regression class was imported. Linear regressor object was created, and it was fitted to train and test. While comparing the score, the training score achieved was 69%, and on the test set, model performed worst. To solve this problem, regression was used. So at the start, from linear model package, lasso class was imported and object was created. So I played a lot with these values, and I thought this was the best result achieved. After fitting this model to dataset, training score achieved was 67%, and the test score also was nearly 67%, not different, and it was much better than 14%, which was achieved for linear regression. In the next part, ridge regression was implemented from same linear model package. Ridge class was imported, object was created, and it was fit to the dataset. Comparing the score with linear regression, training score was same as linear regression. Also, L1 regularization had the same training score, and test score was also same in both cases, almost equal to 67%, which was very high compared to 14%. This solves the problem of overfitting.